Okay, so let's solve this integral over here. So this is an integral that has no analytical antiderivative, so we're going to have to do some tricks in order to get this answer. So the first thing we're going to do is square this integral, and this will make sense in a second. So we're going to take our integral, and we are going to multiply it by itself, because sometimes you actually forget that that's what squaring is, and it's actually not just putting a little 2 up there, right? So the next thing we're going to do is we're going to remember that this x inside of this integral is just a dummy variable. So in one of them, I'm going to change it to be y. We're going to rename x to be y in one of them. And this is a completely legal move because it does not matter what the letter is as long as it's there, right? So now I'm going to see that, okay, this is a double integral. I'm going to rewrite it in that form. So here we go. We've got actually a double integral, right? This is times, and then we have, right, we have minus y squared, and then dx dy. Using some properties of exponents, we're going to rewrite in the following form. E to the minus, oh, I spoiled it, x squared minus y squared dx dy. Okay, so hopefully we can see a little bit of an identity going on here. This little guy here, I already spoiled it. If we remember from some basic trigonometry, if we have a triangle like so, we have x, y, and r. The Pythagorean theorem tells us that r squared is equal to x squared plus y squared. And so therefore this guy over here, this is actually going to be equal to negative r squared. So let's rewrite the integral like that. And the reason I'm doing this again will make sense in a second. We have e to the minus r squared dx dy. And now the variables are not working very well together. We have x, y, and r. And as I said before, we did some triangle work over here. And so that means we're in a different coordinate system. So we have to change the entire thing, right? But I know some things about dx, dy, right? So let me draw dx, dy here. It's a box, right? We have dx, dy, and inside of that is dA, right? This says for some small change in x and small change in y, we have some small change in area. But I can rewrite this in polar coordinates, which is what we're going to have to end up doing. I'm going to draw this guy. Let's do that a little bit better. There we go. So arc length here, this is going to be some radius times some small infinitesimal change in arc length, d theta. And then we're going to multiply this by dr, which is some small change in r, and this is also going to get us dA. So that means when we change out dx dy, we're going to have to change it to be dr d theta. Okay, let's do that. And this is where, if you've taken multivariable calculus before, the r dr d theta comes from, right? But there's something incorrect about this integral still, and it lies right here, right? So before, oh, and right here. All right, so before we were talking about the straight line, the straight lines, the x-axis and the y-axis, that's where we were integrating. We were integrating over the entire real xy plane. Now we're integrating inside of a polar coordinate space. So we have to think, now let's draw the xy plane for a second. Okay, so this is the xy plane. Before we were integrating everything, right? And we're still integrating everything, but now we have to think of it in terms of r and theta. So I know that, right? Like I said, if I'm integrating everything, I'm going to integrate from 0 radians all the way around to 2 pi radians. And I'm going to integrate from here all the way out to infinity, where this is r, right? So that means I'm going to rewrite my integral. This is going to be equal to the total integral from 0 to infinity of e to the minus r squared r dr d theta. And finally, we've arrived at a place where we can actually solve this integral. So let's do that. We could do a little u sub over here. You could probably do this part in your head, but we're going to get this part. We're going to go 0 to 2 pi, and then the integral of this guy is going to be negative 1/2 e to the minus r squared. And we're going to evaluate that from 0 to infinity. Skipping the limit notation here, there's really no need. We don't need to be that concise. This is not an exam. Okay, so we go from 0 to 2 pi, and then we are going to go negative 1/2 e to the minus infinity squared, which is going to be 0, right? And then we have minus the second part of our antiderivative, so we're going to add 1/2 times e to the 0, which, if you remember, is equal to 1, but in this case we're multiplying by half, so it's equal to 1/2. So what do we have here? We have the integral from, let's be careful, we have a d theta over here, right? 0 to 2 pi, the integral of 1/2 d theta, which means we have 1/2 times 2 pi minus 0, which means we have pi. But we're not correct because in the beginning, if you remember, we actually squared our integral. So that means that the answer to the original problem, I, will be equal to the square root